Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Brian Keating, who is a professor of physics at the Center for Astrophysics and Space Sciences at the University of California, San Diego. Professor Keating's research area is the study of the cosmic microwave background and its relationship to the origin and evolution of the universe. In 2001, he conceived the first BICEP experiment, background imaging of cosmic extragalactic polarization, located at the South Pole. Later, he became director of the Simons Observatory, co-located with the ACT telescopes in northern Chile. The project includes over 250 collaborators from over 30 institutions around the world. Welcome, Brian.
Thank you, Gil. It's a pleasure to be with you.
I want to start with your famous experiment at the South Pole, the BICEP. You were looking for the polarization that would exist in the CMB if one of the ideas in cosmology, inflation, that was proposed to describe the smoothness of the CMB is true. Could you briefly explain what the cosmic microwave background is and why the polarization, specifically the B mode, is important to find?
Yeah, so the cosmic microwave background is the universe's oldest light. And we astronomers have very few tools at our disposal to understand what happened prior to our lifetimes and even the lifetime of the Earth, which is over 4 billion years old. We want to understand what happened at the very beginning of time. And the cosmic microwave background allows us to go as far back as possible using what's called electromagnetic radiation, which is just a fancy way of saying light.
Yeah.
And of course, you probably know that light has a spectrum, and along the electromagnetic spectrum that goes from long wavelengths, radio waves, all the way to ultra high energy gamma rays. And in the middle is visible light, somewhere in the middle, and it's a very small window. And we study the universe primarily via a couple of different means, but there's very few ways to understand what happened deep in space and early in time. And one of those is using light. Another way is using neutrinos. Another way is using gravitational waves. And a third way is using meteorites. And that's basically it. There really aren't that many ways of understanding the universe at very early times, talking billions of years ago, perhaps. And the cosmic microwave background is the oldest fossil relic for astronomers who play the role of ancient stellar astrophysicists that are actually trying to be archaeologists.
Yeah.
And so doing the cosmic background radiation takes us back to an age of the universe 380,000 years after the formation of the elements. So the elements were formed what we believe was a very high temperature, very high density phase called the Big Bang nucleosynthesis era, when the elements were formed, the lightest elements on the periodic table: hydrogen, helium, lithium, beryllium, a little bit of that. Mm-hmm. And other than that, everything else had to wait for perhaps millions, hundreds of millions of years to form the heavy elements like carbon that we're made of. And so that epoch when the universe forged the very first elements in nuclear fusion reactions. That took place a few seconds to about 3 minutes after perhaps the origin of the universe in the Big Bang scenario, although we don't know for certain if the universe originated in the Big Bang, and that's where BICEP comes in. BICEP was an experiment that I conceived and co-created with a team at Caltech that we eventually took to the South Pole, Antarctica, the very bottom of the planet. And that experiment was looking not for waves of light specifically, but for waves of gravity. Remember I said there's another relic form of radiation. It's called gravitational radiation.
Yeah.
And those are waves of gravity that have only recently been detected directly with the LIGO experiment. And we were trying to detect them indirectly from an explosive origin scenario where the universe came into existence perhaps as short as a trillionth of a trillionth of a trillionth of a second after the origin of time. And that epoch is called inflation. And if inflation took place, there should be waves of gravity partnering alongside waves of light. And the waves of gravity can distort the waves of light in what's called a B-mode polarization pattern. Mm-hmm. And that pattern, and the subject of my book, Losing the Nobel Prize, is this quest to unravel if indeed the universe had a singular beginning, or as other alternative cosmologies posit, perhaps it's just one of an infinite number of cyclical universes. So those were the stakes that we set out to measure, and the tool that we were going to use to measure it is this cosmic microwave background.
Yeah, so just for my own understanding, Brian, so the cosmic microwave background is the light from approximately 380,000 years post the Big Bang event, and because it is so long back, it's redshifted all the way to the microwave region, right?
That's right.
And we have a picture of that, so to speak, and this was discovered as early as 1964.
Yes. So the cosmic microwave background was actually discovered in data form. It was discovered in 1964, but the results weren't published until 1965. Okay. So it's actually the 55th anniversary. 65th. No, 55th. Sorry, yeah. 55th anniversary. I'm trying to do with only one cup of coffee to do mathematics. Yeah. And because of that, we think that the universe had at least a fiery beginning or an earlier phase. I should be careful not to say beginning, because we actually don't know for sure if time and even the universe itself began at a certain moment. Right. But we do know for sure the universe was at earlier times, was much hotter and denser.
Yeah, so there was a puzzle in the CMB, and that is it appeared really smooth, right? So comet is to 2.8 degree Kelvin, and you don't see much perturbations in there. The biggest perturbation is in the range of 1 in 100,000 or something like that. So it appears really smooth, and correct me if I'm wrong, and that could not really be explained from the concept of a Big Bang. Is that right?
Well, it could and it couldn't. Yeah. It's not that the Big Bang itself is incompatible with the smoothness. It's that the Big Bang alone is not compatible with the smoothness, the lack of fluctuation sizes in these amounts of radiation that we receive from all different locations in the universe. And I should just say for listeners that might not be familiar, if you're standing on a at the center of a stadium and a baseball stadium, if you will, and the crowd is there because coronavirus is over, and and the pitcher is standing there, and he looks, and every single person is holding a light bulb, and their light bulb is set, or their cell phone flashlight is set to the exact same power level. Yeah. They all have the exact same intensity, no matter where he looks. Then that would be said to be a very isotropic distribution. Now, that could be accomplished in a couple different ways. You could have told the people, let's say color, because color is a little bit easier to visualize. So everybody set their color of their screen on their cell phone to be the exact same color. Yeah. There's tiny variations in that, but the human eye can't really pick up and perceive variations when they become too slight. So to the picture, it looks like they're identical, almost perfectly smooth. Now, how did it get to be that way? Well, you would have to say if there's 100,000 people in the stadium or whatever, that they would have had to communicate. Somehow they would have communicated before they came in. Now, what if I told you that they were instantaneously teleported in and they never had enough time to actually communicate with one another? And then you'd say, well, that doesn't make sense, because the speed of light to communicate across the stadium, might be a fraction of a microsecond. And that microsecond timescale is just simply too short a timescale for them to all synchronize this color, this conspiracy to take place.
Yeah.
So if you believe that the Big Bang took place and it was indeed the creation of time, then something like inflation must have been required in order to achieve this remarkable uniformity and smallness of the size of perturbation. So the fact that the universe to our microwave eyes looks perfectly smooth, almost perfectly smooth, but not exactly perfectly smooth, if you will.
Right.
And that's important. Yeah, go ahead.
Yeah, and so the puzzle is there isn't enough time for light to travel from one end of that picture to the other. It's 90 billion light years or so. And so there isn't enough time to have information, to pass through, and hence they couldn't really synchronize that information, and hence so that was the puzzle. So inflation was proposed as a way to explain that, and inflation is a very rapid expansion of the universe, very close to the origin, right? 10 to the power minus 36 seconds or something like that.
That's right. Yes.
And, yeah. Go ahead.
Exactly. So what typically happens in cosmology, and often in physics as well, is that there'll be some model that, say, the solar system is centered on the Earth, and that will comport with evidence until more data comes in, and then there'll be more evidence, and that evidence will then sway people perhaps to correct the model and add some corrections to that model, and you'll add epicycles, et cetera. And then eventually someone will come around with a whole new paradigm and say, no, the Earth is not the center of the solar system, the sun is. And then there'll be evidence for that. But then that's not exactly right, as we know. The sun is not the precise center of the solar system.
Right.
And even if it was, there was a conjecture that the sun was the center of the universe. So we keep going through these things. The center of the galaxy is centered on the sun. We know that's wrong. That was believed for a long time. The Milky Way galaxy is the center of so we keep refining our models until we really don't understand a way to add to the model without subtracting from the model. And so in the case of the Big Bang, which was proposed in the 1920s and 30s, this model carried the day for a long time. But in the 1980s, it was perceived that there were these problems, these paradoxes, if you will, that could not be understood without introducing inconsistencies tantamount to effectively requiring a whole new paradigm, just as the heliocentric model supplanted the geocentric model. Yeah. And this is the theory of inflation, as you say.
Yeah, so you proposed, I can't remember, this was when you were at Caltech, right? So you and your team proposed that if at the origin there should be a big gravity-related event, there will be huge gravity waves, and if that is true, there should be some sort of polarization in that CMB in that CMB radiation, right? So if you can find that polarization, then it gives additional credence to the theory of inflation. It won't prove it, but at least give it additional credence. Is that the idea?
Yes, that's right. So it's very hard to prove something in physics. It's not mathematics where we can actually come up with a construct that starts with some number of axioms and then derive inarguable deductions from it. Physics is not possible to do that. Instead, what we can do is falsify other predictions and prove them wrong. Yeah. And then what you're left with, as in the case of the geocentric to heliocentric, and then heliocentric center of the galaxy to non-center, etc., is to exclude models that don't comport with the evidence that you acquire. And I'm not a theoretical cosmologist like Brian Greene or Neil deGrasse Tyson. I'm an experimental cosmologist. So what I'm looking for are departures from data that can only be explained in the context of some larger theory that makes predictions and gives me a likelihood for how sensible, scientifically appropriate for you, the context of my data is in the interpretation of a model that's been proposed.
Yeah. And so the BICEP 1 was the first experiment. And interestingly, you did find something, even though the actual reasoning behind that was different from what you expected.
Yes, so we actually set out, in fact, to measure these waves of gravity and their imprint on the microwave background's properties in terms of its polarization, which is a property at least known of the properties of light. People know its color, people know intensity, but they rarely understand polarization. But it's just one of the three properties that each photon has.
Yeah.
And that polarization would owe to the interaction between waves of gravity and waves of light. And additionally, the matter that's present in the early universe. This is 300,000, or 380,000 years after the elements were formed. And that origin, would imprint them with this signature. If inflation took place, there'd be these waves of gravity. Furthermore, if inflation took place, there was a concomitant expectation that there's something called the multiverse, which we can get into later, perhaps.
Yeah.
And that is a very startling conjecture that just as our planet is not the only planet, our sun's not the only sun, galaxy is not the only galaxy, our universe is not the only universe. And so the theological, philosophical, scientific implications of what we were studying could not be higher. And we set out to make this measurement precisely to see that, if we could gather more and more evidence, as we called it, it was sort of the smoke from the smoking gun. In other words, if inflation took place, there was tons of circumstantial evidence. But, if you're trying to solve a murder case and it involves a gun, but you can't prove the gun actually went off, you don't have much of a case. It doesn't prove, who was the murderer or whatever, but it at least dictates that certain events took place. So for us, the explosive bang that we were looking for was really this inflationary spark that lit off the explosive origin of the universe if the Big Bang did take place.
Yeah, but the measurements were due to something else? The actual findings? Yeah.
So what we looked for was we set out to measure the waves of gravity. We knew there were always potential sources of contamination, both from the instrument, from the location, from imperfections in the optics, for example, and even from our astrophysical objects that weren't objects that we were interested in studying. Namely, our galaxy is suffused with sources of microwaves that can easily contaminate the results that we're looking for and overwhelm them. And in fact, the signals that we were most worried about were those from the emission of what's called cosmic dust, or dust in the Milky Way galaxy itself, which is really very familiar. If you've ever seen a meteor shower, you've seen cosmic dust in action, because meteorites are really leftover relics of the early solar system. Remember, I said that's one of the few pieces of information that astronomers actually get brought to Earth to them. We can't go out and do an experiment and see, what would the universe look like if the sun were, 1,000 degrees warmer. We can't do that experiment. We can have theories about what would happen. But so we knew that the Milky Way galaxy is replete with sources of interstellar dust, which is the product and the leftover byproduct, if you will, of the death of a generation of stars that existed perhaps billions or at least hundreds of millions of years ago. And this dust is present in all locations, and it has a well-known distribution that it decays exponentially the farther you get above the galactic plane. So have you ever seen a picture of the spiral galactic structure of the Milky Way? Taken, kind of a selfie taken from, billions of light years away. No, we can't actually take a picture of the Milky Way galaxy, but we can look at other galaxies like Andromeda. And we know that they have a spiral structure. They have a bulge at the center, and they kind of extend vertically and the positive and negative directions above and below the galactic plane, there's tremendous amounts of failed stars, dead stars, supernova remnants, etc. And there's a tremendous amount of dust in the Milky Way galaxy. Mm-hmm. Well, that Milky Way galaxy dust can be aligned by what are called magnetic fields that are threading their way through the Milky Way galaxy, producing this curling, twisting pattern of microwaves that we call B-mode polarization, and perhaps exactly mimicking the signal that we sought. So we knew about this signal, and we didn't know that it would be the most limiting potential contamination. We thought the measurement was so hard to do that we never achieved the sensitivity when we first proposed the instrument, that it would be almost irrelevant. And if we did detect something, we could always go back and see if it was dust or if it was gravitational waves.
Yeah.
And of course, the title of my book is Losing the Nobel Prize, not winning the Nobel Prize. And so it's a spoiler alert there. But the fact is, we ended up measuring contamination from dust grains in the Milky Way galaxy, exactly aligned with the pattern that we would expect if inflation took place, and that we were incapable at the time of the announcement of ruling out. Nevertheless, even though we knew about it, we tried our best to rule it out as best as we could, and we still went ahead with the announcement, much to the chagrin of ourselves later when we had to retract the claim that we had detected the first evidence ever in history for the inflationary explosive origin of the Big Bang.
Is it possible from the data, can you reprocess the data to get to what exactly you're looking for, or you need additional experiments?
So when you have what this is called a type of systematic error, or error in the and it could be either in the instrument, you could have some source of excess noise. Don't forget, Gil, the type of measurement that we were trying to do is so fantastically difficult. It's much harder than looking for like a bright light bulb on the surface of the moon, because right. What we're looking for is a signal that's perhaps 1 billion times fainter than even the cosmic microwave background temperature, which is a frosty minus 270 Kelvin in Celsius, rather, or very close to what's called absolute zero. It's about 3 Kelvin, the microwave background as a whole. But the signal we're looking for is a fluctuation of order tens of nanokelvin. So billions of the size of the already minuscule size of the microwave background itself.
Right.
So this is a very challenging experiment. We thought that we would be limited by the experiment itself, or even the frigid South Pole, because even at minus 100 degrees Fahrenheit, or 80 Celsius or whatever, it's still billions of times hotter than the signal that we're looking for. So honestly, we thought we would be stopped by that long before we were stopped by an astrophysical source. And so we didn't make a blunder. I always say we didn't leave the lens cap on or put our thumb on the lens. Didn't do that.
Yeah.
But instead, we saw basically what we had been looking for, which sounds, well, what's wrong with that? But a lot of times in science, when you set out to look for something, you're subject to a type of bias that leads to prejudicial interpretation of results, not incorrect, fudging the data intentionally or even overlooking errors in the instrument. This is truly a detection of spectacular sensitivity and a huge technological leap forward that has not even been matched remotely by other projects in the half a decade since we announced the results in 2014. So the signal that we look for, we ended up finding the exact same signal that we were searching for, but it turned out the source of that signal was not the source that, in all honesty, I had certainly hoped to detect, and I know other people did as well.
And the project is continuing, right? So you had BICEP 2, BICEP 3, additional things going on in that area?
Yeah, so that came later. So BICEP 2 is the experiment that we used that announced the findings that made worldwide headlines and whispers of Nobel Prizes.
Okay.
That experiment was the successor to BICEP, which I had created in 2001.
Yeah.
And then after BICEP 2, results were basically retracted, and the conclusion was retracted. We realized that in order to remove the contaminating signal, we couldn't go into space with a giant vacuum cleaner and suck up all the dust that's in the Milky Way galaxy. Right. But we could do another experiment that was only sensitive to dust. And then when you have a signal that's only sensitive to dust, you can then subtract those data from the signal that BICEP 2 detected, for example, which contains, we know, dust plus a potential amount of cosmological B mode signal from the inflationary epoch.
Right.
So the combination of cosmic C plus dust D, we could then subtract from it a measurement only of D, of only dust. And what we're left with would be the cosmological signals if they're there. Right. And that's what BICEP 3 is doing, or did do. And now the team is on to a 4th generation, not called BICEP 4, startlingly. It's called BICEP Array, but it continues at the South Pole. And then there are many collaborators and also competitors that are seeking to detect the very same signals. And I'm co-leading with 3 other scientists at Princeton, Penn, and Berkeley, the 300-member Simons Observatory, which is an enhanced version, perhaps the biggest, most ambitious experiment of its kind ever devised. But again, Gil, it's trying to measure the cosmic signal plus the dust signal, and not only the signals that we're searching for from the universe's origin.
Right. And Simons has broader objectives, right?
Yes.
If I understand it correctly, one of them is this issue with the Hubble constant. We get different values from different approaches to Hubble constant. And are there things that you're doing at Simons that might alleviate the problem?
Yeah, so that's a very astute question. So one thing that we're doing with Simons that we can't, and it's pronounced Simons, Gil, by the way, just in case you ever meet Jim Simons. I don't want you to miss your opportunity to talk to the world's smartest billionaire and call him by the wrong name. So yeah, with Simons Observatory, what we're trying to do is measure, as I said, the cosmic signals from inflation, potentially from inflation, which would then rule out these competitor theories, such as the cyclic model that Roger Penrose has proposed and a bouncing model that Paul Steinhardt has proposed. So that would falsify those models and, if not prove inflation. We're measuring dust. We're also measuring properties of the Milky Way galaxy itself. And we're doing something that BICEP couldn't do, because when I designed BICEP, I wanted it to be the simplest, cheapest, easiest experiment of its kind. And in astronomy, there's no simpler telescope than that which Galileo first used in 1609 to look at objects in the universe for the first time telescopically. Mm-hmm. And that is a refracting telescope, a telescope made with lenses and only lenses. Now, because of that, because of the fact that you can only make a lens of a certain diameter before it starts to take on many, many deformities and deficiencies, we knew that we would only have, by virtue of the limited diameter of the lens that we could build, about 30 centimeters across, was the largest at the time, we would never have the angular, what's called the angular resolution, to measure the fine scale structure of the cosmic microwave background. Mm-hmm. And in so doing, we would miss out on, say, measuring the properties of galaxies and dark matter, things called neutrinos, and we would not be able to measure those with BICEP. That was fine, because that wasn't my goal. My goal was just to measure these inflationary, gravitationally generated B modes patterns. But now with Simons, we want to do both more and better. So we want to do a better job than BICEP 1 and BICEP 2. And we're really in a fierce competition with our friends on BICEP Array. I'm not involved with that project, but I am still on BICEP 2. And so we want to do the job and compete with them for 2 reasons. Not just to get there first and win a Nobel Prize. I personally have come not to care as much about the Nobel Prize as I once did, and we can get into the Nobel Prize later. Yeah. But basically, the other reason is that when one experiment makes a claim, it's going to be suspect no matter what. And especially when it's the same team that made the first claim of the first detection originally. And that's not a knock on my friends on the BICEP team, but rather it's just a statement of the way that science requires independence and verification. And so by having 2 different teams measuring the same signal, that will be much more confirmation of the validity and the credulity that you should have in those signals. So I think it's a wonderful time to be in this field. There's a lot of attention, and the reason is clear, because we're really trying to unravel whether or not the universe began with this explosive inflationary origin. And the other technologies that we have a massive 6-meter diameter telescope at the Simons Observatory in construction currently in the high Atacama Desert of Chile. And that project, or at least it was before COVID shut down the whole country of Chile, but they can talk about that some other day. Hopefully that'll clear up. But that telescope can resolve features, 1/60th as wide or higher resolution than BICEP could. So it's a phenomenal instrument, and it will allow us the opportunity to measure a guaranteed signal, which is this impact of neutrinos and their masses on the formation of structure in the universe.
Yeah, you mentioned, before we leave this subject, Brian, you mentioned multiverse. So if inflation is true, the hypothesis is that you can really get the Big Bang followed by an inflation without a multiverse type construct. Is that the idea?
Um, yeah, so there are alternatives
Yeah.
to it, but the question is, can you repeat the question? Sorry, I'm
Yeah.
sorry.
So my understanding is that if inflation is proven to be true, not complete proof, but high level of confidence, inflation coupled with Big Bang is actually true, then that cannot happen in a vacuum, right? It can only happen in a multiverse type construct. It would have happened many times in that way. Is that the idea?
Yeah, the question is a good one. The multiverse comes along for the ride in
Yeah.
most of these, and that is sort of a byproduct of the mechanism that creates in the inflationary scenario in the first place. And that's called quantum field theory. And we don't have a lot of time to go into that.
Sure.
But suffice it to say that in physics, we believe that the instantiation of particles, and including the photon, which is just the name we give to the particle of light, are created owing to the fact of of what's known as a quantum field. And there's many different types of quantum fields. But the inflationary universe posits a quantum field that's called a scalar field, and it's not unlike the Higgs boson in certain senses, but we'll leave aside that for a second. And it means that the universe was suffused with a type of energy, and an energy that depended on position, and energy that depends on the configuration of this field in this abstract space. And that every point in space-time had this value of the field.
Yeah.
And the space-time is greater in dimension, perhaps even physical dimension, meaning that it could have more than 3 dimensions of space, for example, but we won't get into that.
Sure.
But it had a greater extent in 3 dimensions than even the observable universe that we can see today, extrapolated backwards in time by the appropriate factor. So in other words, there could be a vast array of other universes that were created, if you will, at the same time, but are so far away that light simply not had enough time to traverse the distance between them. And because of that issue, that makes it basically impossible for us to know whether or not they exist. Now, they could be separated by a light year from our universe. In other words, the closest universe in this abstract space, in this all of space-time itself, the locus of all points in time and space. There could be a universe with galaxies and podcasters and so forth. And that could be 1 light year away, and we won't know about it right now, but we'll find out about it this time next year when our universe encounters the signals transmitted from that universe, for example. Now,
So that is possible, that you can transmit signals from one universe to another.
Yeah, so theoretically, there are papers written by colleagues and friends that have made predictions that actually another universe could leave an imprint on our universe. That not that we could communicate. That I think is a little far fetched. I mean, we cannot even communicate on a reasonable timescale with an intelligent life form if there's one within a dozen light years of Earth, because there's simply no evidence for such a thing taking place. And actually there's I had an interview on my podcast recently which suggests that the closest civilization to the Earth that could exist in the Milky Way is something like 10,000 light years away. So that would mean a 10,000 year long one-way communication. So it's quite impractical, let alone we're talking 90 billion light years. But there's a potential that, over time, a pattern could emerge that we would see the imprint of our universe's last scattering surface or Big Bang surface that would then impact with another one, and that would leave a characteristic telltale pattern, according to these scientists. So that would be direct evidence, if you will, of a multiverse in some sense. On the other hand, the microwave background B-mode polarization would be indirect evidence if it's owed to inflation, because of the fact that inflation is very hard to turn off. It takes a very, very finely tuned set of properties for the universe to expand, so much so that you can then have all different parts of the universe have the exact same properties, and but not expand too much that it just runs away forever and just inflates away to nothingness. And so the mere existence of the inflationary B modes in our universe was taken as essentially as close as you could get to indirect proof that the multiverse scenario exists, by virtue of proving that the inflaton, this inflation quantum field, exists. So that's the logic.
Right. So, but the Big Bang plus the inflation is just one theory,
yes.
right? Although it is largely, it's the best accepted theory, I would imagine. But there are alternatives like the cyclical theory, which is, so that does not require a Big Bang. That is, it's almost continuous, right?
Yes, that's right. So that it basically doesn't shut off. That's exactly right.
And so it doesn't shut off, but it's also many waves of universes. I mean, it's essentially sort of like a multiverse, but it is happening over and over again.
It is, if this is true, it's happening throughout this greater extent of all space-time called the multiverse. Yes, so there'd be universes that could come into and out of existence. Some could live much longer than our universe. Some could dissipate after nanoseconds. And so it presents a problem that essentially all different forms of universe are possible, meaning that there literally could be a copy of our exact universe located at some tremendous distance from our universe, in which everything we're doing in our universe is taking place. And then there could be a universe where I have the Scientific Sense podcast and you have the Into the Possible podcast. Because infinity is a very large number, and so all these different combinations would play out in the multiverse. So that gives people a lot of trepidation, because it's felt that is no longer scientific. If you ascribe the ability for every possible event to take place, then there's no combination of experiments that could prove that hypothesis wrong.
Right, but the multiverse that is hypothesized from the Big Bang inflation paradigm, that is different from the multiverse that happens in quantum mechanics, right? If
yes,
every time you make, right?
There are different multiverses. So we should also be careful to point out that what you're talking about is called the many worlds interpretation of quantum mechanics, which says that at every moment there's a branching of the wave function of the universe, which contains within it every particle, every system of particles, their wave functions, and that has certain properties, and then that wave function splits into a very large number of potential wave functions, which, if measured, could take on a large value of different ranges of parameters for the universe. So in one universe, you could make a decision, that would lead you to do something else completely in your career that happened 20 years ago. And then you're actually living in that branch of the wave function somewhere else. We don't know exactly where that would be. Is that, because the Earth is also a set of particles, and the Earth is a set of, and then those particles would have their own interactions with this many worlds interpretation. So there's a great deal of speculation about that. But yes, that is a completely separate type of multiverse, if you will, in the classification scheme that physicists use. And it's possible to have hybrid combinations. So you could have a multiverse in space, and then within that you could have certain universes. You could have our universe, then you could have a copy of our universe, And in our universe, the many worlds interpretation is wrong, but in the other universe, the many worlds interpretation is right. And you could see that these possibilities are very interesting, but they're also very frustrating.
Yeah, and our own universe, one could imagine, since we don't have a clear idea how big it is, it could be infinite in itself. We could have regions within our own universe that could be considered different universes almost, right? Because there'll be no communication between them.
Yes, that's right.
So another topic that I'm always fascinated by, Brian, and I know that you have some ideas around that, is free will.
Yes.
Does that exist?
Okay, so that's a big that's a big question. The concept of whether or not the universe possesses what's called superdeterministic features, in that every single event is foretold or for encoded back perhaps at the Big Bang, is an
Yeah.
open question. And then a great deal of people nowadays has become extremely popular that indeed there is no free will because of this determinism, because at the fundamental level there are only properties of particles, and those particles are fungible, and you could replace every proton in your body with every proton in my body, and you wouldn't be able to notice it, for example. But now the question is,
Right.
how does that affect human beings? And if you think of human beings purely materialistically as just a collection of protons, neutrons, and et cetera, then yes, you might be led to that conclusion. I personally am not interested in this question because, to me, I'm a behaviorist. I like to look at people's behavior and ask the question: are they acting as if they have free will? And if they do, then they are responsible for their choices. And I see no reason to let people off the hook for their moral choices that they make based on the supposition that something might have happened in the Big Bang. Any more than I would say, I'm going to blame your father for you cutting me off on the road, today in traffic. Is that your father's fault because he had you, and your mother? No, it's you
Yeah.
made that. You actually chose at that moment. Whether the choice was foreordained 13.8 billion years ago is another question. But I'll also point out that there's no guarantee that even the Big Bang took place. We
Right.
actually have, we have very eminent theoretical physicists who claim that there are alternative models, shall we say, not that we throw everything out, but that there are alternative models that do not feature a single origin of time. So I would like to know, what is the origin of free will in a cyclical universe? And that's an
Right.
open
Right.
question. So I think it's
Yeah. So that. Sorry. Go ahead. Sorry.
um, anyway. Yeah.
No.
Mm-hmm.
No. No. Well, I was going to say, the thought experiment that I sometimes get into is, yeah, if we can go back and forth in space, and we can go back and forth in time, let's say, then one could imagine a situation that the whole space-time construct is done. It is sitting
Mm-hmm.
somewhere, and you're just moving in something that has already been done. So in that context, there cannot be free will. I don't know if that is a way to think about it or not.
I've heard that. Is that related to the block universe kind of conjectures?
Yeah, yeah. I mean, if we are just moving in a space-time construct that is already out there, and we are today at this space-time coordinate, and we could, if we go move back and forth in time, it would imply that a future time and future space-time in that arena already exists. We're just moving into it.
I guess I worry
Yeah.
about, does the block universe concept incorporate the multiverse? For example, what if there were there is the multiverse, which, again, I'm not a huge fan of the multiverse either, but since you brought this up, I'm
Yeah.
gonna flip the tables on the interviewer becomes the interviewee now, Gil. So I want to ask you, if that's the case, and there's a multiverse, and that we know about
Yeah.
long range correlations, we know about Bell's paradoxes, etc., then how can you say that there's no influence of another block universe within a multiverse operating on the block universe that we claim is our only universe, our perceived observable universe?
Yeah, I mean, one could argue that all multiverses are also block
You mean
universes.
all
There are also
universes within the multiverse? Because there's only one multiverse,
yeah,
because
yeah, all universes in the
Mhm.
multiverse. So there could be. I know nothing about this, Brian.
Okay.
I'm
Well, you
just
brought it up, so
I'm
I
just
thought it's fair
uh,
game.
s- s- yeah, speculating that there could be a situation where everything is done, everything is in static mode. They're just sitting there. The space time in a variety of universes are just sitting there, and we have an opportunity to move in them. In which case, you cannot really change anything.
Yeah. Well, I always wonder about the impetus for why these are attractive. In one sense, if I said to somebody like my friend Sean Carroll, who believes in a lot of these, deterministic, as far as I understand, his concepts of free will, et cetera, are
Yeah.
similar to the ones you're describing, but I know he's got a very low level of credulity in a supreme being, such as a traditional God in an Abrahamic sense.
Right.
So I've asked him this in person. What is your credulity that you ascribe to the multiverse? 50-50,
Yeah.
50-50. And then I ask him, what's your probability that you ascribe to God? And he'll say less than 5%. So he's too smart to say zero, as is Richard Dawkins. So he won't say zero either. But the point is, in that case, what is actually a meaningful question to ask,
Yes.
because I
Yeah.
think if everything is super determined, then there's very little functional. Yeah, you don't have to believe in some guy with a white beard perhaps floating around in space, but if everything's foreordained, then there really is no need to hold human beings accountable. There's nothing unique about human beings. And I've heard people argue that even protons have consciousness, and it's called
Right.
panpsychism, et cetera. So I feel like, in a practical sense, those are very unfulfilling arguments to make. And what I care about
Yeah.
is practical. So example I give is, there's no way for you, Gil, to verify the block universe, even if or Sean Carroll or
Right.
whoever. Right? You can't verify that. It's a construct that we use to play out Gedanken thought experiments. On the other hand,
Yes.
you could imagine that there are certain things that you could test about the Bible, right? I mean, there are things that the Bible makes predictions about, if you will, and yet I don't see anybody who's scientific taking us up on that. Like, let me try to lead a religious life and tithe and honor my parents and then obey the Sabbath and whatever. But
Yeah.
they seem much more willing to kind of entertain these things which cannot be in principle tested, versus things that they could actually test, but they dismiss it out of hand with a prior probability as close to zero as you could get. So I just find that interesting as a sociological observation of my friends, that
Yeah.
to be atheist
Yeah.
instead of agnostic, in the face of such a question, and to dismiss it as childish or worse, perhaps.
Yeah. So religion and cosmology. Let me throw this back at you, Brian. They actually share some common characteristics. So we don't really have a very good idea. Let's say Big Bang theory is the top theory. We don't really have a very good idea of what happened at time equal to zero. And so it is purely a hypothesis. We make some observations, we do some experiments, and we say some experiments actually fit with the theory. Um, religious, and I'm not religious. Religious people also do similar things, right? So they don't really have an answer to God, and they make some observations. They run some experiments. For example, praying could be considered an experiment. Granted, it's not randomized, placebo-controlled trials, but they could do that and prove or otherwise, right? So, would you say there are some characteristics that are common between religion and
Oh
cosmology?
yes, yes, and for a very long period of time, even the great opponents of the Big Bang model, perhaps no one more formidable than Fred Hoyle, who actually
Yeah.
coined the term Big Bang as a pejorative, which you may know from
Right.
perhaps encounters with British English, which is a pejorative term. I won't get into that, but that
Yeah.
was meant to really mock the concept that there could be the singularity, this infinitely dense, hot state of the universe's ultra early origin. And he thought it was preposterous. And when asked why does he think cosmologists adhere to it, he said the following. He said, I think that cosmologists are overwhelmed by the belief in Genesis 1:1. Namely, he claimed that the only reason cosmologists were believing in the Big Bang, as opposed to his quasi-steady state theory, was because they were God-fearing. It's preposterous. I think nowadays, 90% of the National Academy of Sciences are either agnostic or atheist. 10% actively affirm a higher being, but to what extent that really means. So absolutely, there's always been this, as I point out in my book, Losing the Nobel Prize, the kind of main reason why I think cosmology engenders these huge subjects. I mean, look at all we talked about today: quantum mechanics, consciousness, free will, Big Bang, multiverses, many worlds, all those things. Now, I love my colleagues who study, higher order phase transitions in certain types of magnetic fluids. They're brilliant people, smarter than I am. But they don't get up and think about, well, what's the philosophical implication of this fluid that has some iron particles in it? What does it have on the question of free will or God? It's just they're not concomitant with them. And it's not to say that they don't think big thoughts. I'm just using this to point out that cosmology has always engendered fierce patterns, and ever since, you can even say the Bible itself. Why does the Bible, which is, I know very well, I can actually read the Aramaic that it was, and Hebrew that it was written in. Why does it begin with Genesis? It's really, or the origin of the universe. It's really a book of laws for a tiny sect of nomadic, Semites in the Middle East, that make up 0.2% of the world's population. So what does that have to do? Why would you start that? Like, if I'm making an origin story, a modern origin story, I don't start with, for the baseball team that plays in San Diego, the Padres, I don't start with the Big Bang. I start with, 1969 when they started. So I think it says something about the high stakes that are involved and engendered whenever we talk about the origins of things. And that even plays into your own life. I mean, what I always ask people, what's the most important day in the calendar to you, Gil, personally?
My wedding.
Yeah,
perhaps.
your wedding. Some people say birthday, but what was your wedding? It was the beginning of your marriage, and it was the beginning. And so in the beginning is a very powerful psychological force on people, as well as an interesting physical subject to study.
Right. Yeah. I want to get into your book also, Brian. So especially you have some objections around the Nobel Prize
Indeed, yes.
process.
Yes.
Right. Let's talk a little bit about that.
So my book, Losing the Nobel Prize, is written in response to the events that took place around the BICEP 2 claimed discovery of inflation, which, as we just said, meant the multiverse was a likely result of such a discovery if it panned out. I knew when we made the announcement, for a variety of reasons, that I wouldn't win a Nobel Prize, either because we were right and another team, another segment of the team had kind of removed me from the leadership of the BICEP project, but also because if we could be wrong, as we later turned out, in which case nobody would win the Nobel Prize. So in the first case, someone else from the team would win it, even though I had created the experiment's predecessor and led this concept. For a variety of political and science sociology reasons, I had been removed from the leadership of BICEP 2. And I describe a little bit of that in the book and the impact that had on me as a human being. The book is mainly a memoir. It's not really only a popular science book. It's not only a polemic against the Nobel Prizes, but it does have a second meaning. Losing the Nobel Prize also connotes the fact that we should lose certain aspects of the Nobel Prize's current status, which is that it's highly exclusionary. It's highly biased. It tells a very distorted picture of how science takes place and how science is conducted, and it offers an incorrect image of what a scientist really is. So, in 3 of the book's 11 chapters, I describe failures of the past Nobel Prizes to live up to the lofty ideals that Alfred Nobel set for them. And so, so indeed, the book is sort of mostly a memoir, a lot of popular science, philosophy, religion, but it's also kind of a call to arms to save the Nobel Prizes while there's still time. Today, I was on the phone with the BBC. We're helping them with a project they're doing for this fall when the Nobel Prizes are released. And the author of the story was really, she was intently, curious about these different failures of the Nobel Prize to live up to what Alfred Nobel really wanted them to be, and how they've come to really, as I said, to negatively depict how science is done, both in the character of the way the prizes themselves are given, and certain failings that they have to recognize the triumphs of science and groups of scientists in particular operating behind the scenes in the shadows.
Yeah, maybe what we need is not just a re-engineering, but maybe instituting a new type of price. Because I think, in this modern era that we are in, things have changed, right, quite dramatically. So, what impacts society is very different from, say, 7,500 years ago.
Yeah, exactly. There is a huge difference. And other institutions have made changes to rectify the injustices of their past awards. And I think if the Nobel Prize wants to remain relevant, there's no law of physics that says it has to remain so important forever. And if they're not careful, this billion-dollar business that's integral to Sweden's identity, so much so that the holiday that commemorates Alfred Nobel's death is like a national holiday, December 10th, and that's the day they give the awards out in the nation, in the capital city of Stockholm.
Right. So in conclusion, Brian, if you can return back to Simons,
yes,
and your work there, if you look forward 5 years, what would be the most satisfying discovery for you, or the most satisfying outcome, more generally?
Yeah, so it's interesting the way that you ask it, that it'll be satisfying rather than what do I hope to discover, and that's usually what I'm asked to discover. and the problem with that latter formulation is that it presupposes there'll be a discovery when there's no guarantee that anything new will be discovered, and that's part of the risk that we take as scientists. I think for me, what I want to do is answer the biggest questions. So if there to shed light on this, no pun intended, I think it would be a tremendous discovery to understand if the universe began in a singular origin. As I said, the religious doctrine really does prescribe a single origin of the Big Bang, in that there was a beginning. That's the very first word in Hebrew. Bereshis means in the beginning. And so you can't have a beginning if the universe is eternal. And so for me to discover that would be for me to put the Bible to the test, in a sense. And that's a very interesting thing to do. And there aren't many opportunities to do that. So now I don't think of that as the only reason I'm doing it, but I think discovering properties of the expansion and the what's called the Hubble constant that we understand, it governs how the universe is expanding, the rate at which it expands, and how that's related to the composition of the universe. There are these ghostly particles called neutrinos that suffuse the universe, also owing to the Big Bang epoch. We know they're the only fundamental particles that are indivisible, but contain information about their masses via their imprint on the Big Bang's microwave background. And we're not able to currently measure what their masses are. We know that they have mass, but we don't know what the exact mass is. And so that's almost a guaranteed signal if we do everything right, based on other experiments have told us there's what's called a lower limit. So I'm very hopeful that we can build an experiment that's capable of returning at least that, a guaranteed signal, while we look and swing for the fences. So it's kind of hedging my bets. There are signals that I expect are there and that we will measure with extreme accuracy. We'll learn much more about the Milky Way galaxy that we live in. And we'll learn a tremendous amount about these elementary particles whose properties are heretofore unknown. So those are kind of guaranteed signals. And then there's this, really the ultimate chase of all is whether or not the universe had a single Big Bang or not. And that I don't like to say I hope I'll find, but it would be a very satisfying thing to know the answer in my lifetime.
Right, right. Excellent. Yeah, this has been great, Brian.
Thank you, Gil.
Thanks so much, so much for spending time with me, and good luck with all your experimentation. This is in Chile,
This is
right?
in Chile. Yeah, it's at
Yeah,
17,000 feet above sea level, 5,200 meters in the Atacama Desert of northern Chile.
should be a nice place. If you get back to the East Coast, look me up as well.
I'd love
I'm
it.
not too far from Providence.
Yes, yes. I go back home frequently, and I'll be sure to be in touch, Gil. Thank you so much.
Excellent. Okay. Thank you. Bye.